Hello, students. My name is Ravi Ranjan Kumar, and I welcome you all in this lecture. Today will be the last lecture in the series of discussion of center of mass and collision. And in the previous two sessions, we discussed about the center of mass, how to find out the center of mass of a uh, system of particles and continuous mass distribution. And then we looked at motion of center of mass, for example, velocity of center of mass and acceleration of center of mass. And we looked at how those concepts can be used to solve several problems, several model of problems. Okay. And then in the previous class, we looked at the nature of collisions. Okay, like how collisions can be of two categories depending upon the line of impact. And the collision will be either head-on or oblique. And then on the basis of energy, we categorize the collision into two categories again. Okay, whether the collision will be elastic or inelastic. We define several physical parameters like coefficient of restitution, okay, which would be very, very important to analyze the collision, the condition of collision, uh, the condition before collision and after collision, etc. So in today's session, what we are going to do is we are going to look at the collision in center of mass frame. And looking at the collision in center of mass frame sometimes makes a given problem surprisingly easy. Okay, and since this is the final session of final lecture of this session, so I will also be discussing about some general questions which appear in exam quite frequently, some general model of problems, okay, which will be useful. Okay, so being said that, let's start our lecture. So let me share my screen with you people. So here it is. Sure. Okay. So collision in C frame we are going to discuss. So what we can say over here, the situation we are going to study is first of all we will study about head-on collision. One by one we will study. So let's start our discussion from head-on collision. Okay. Okay, so let's take the case scenario first. We will be looking at the situation in, let's say, in ground frame. So in ground frame, let's say we have two particles of mass m1 or two bodies of mass m1 and m2. And let's say body 1 before collision is moving with some velocity v1 and body 2 is moving with some velocity v2 over here. Here during this discussion we will be using this notation that before the collision I have written the velocities and v as v1 and v2, and after collision we will be writing the velocities as v1 dash and v2 dash. Means v1 dash or v2 dash, whenever we are using this dash sign over here, that means we are looking at the condition after collision. Okay, so here throughout this discussion we will be using this symbol. So v1 dash and v2 dash are velocities of m1 and m2 respectively after collision, where v1 and v2 are before collision. Okay, so the problem statement is basically knowing the condition before the collision. Okay, will we be able to find out the condition after collision? Means we are looking for like what would be v1 dash and what would be v2 dash. We know how to solve this problem in ground frame by using conservation of linear momentum and equation of coefficient of restitution. So here, this problem we are going to discuss head-on collision, and we will take this specific case to be elastic collision over here. Elastic collision means the coefficient of restitution is going to be equal to 1, or you can say there would be no loss of kinetic energy due to collision. So this is what the picture looks like in ground frame of reference. Okay, so in center of mass frame of reference, when we are going to look at the same situation, how is it going to look like? So in center of mass frame, in C frame we can say, and let's recap a few discussions, a few points which we discussed in the first lecture of center of mass. In C frame, let's say we have two bodies, okay, a particle m1 and m2. Okay, in ground frame they were moving with velocities v1 and v2, etc. Say, so we learned that the linear momentum. Okay, so say p1. Okay, and we will use one more symbol whenever we are looking at a physical quantity in C frame. We will be using this tilde sign, like p1 tilde means that is linear momentum of 1 with respect to C frame. So this P1 will be equal to minus P2 that we have learned already. Okay, and if you are not aware of this, please go see the lecture number 1, which is related to center of mass. In that I have discussed the center of mass frame, and also in that lecture we learned about the since the since the p1 and p2 vectors are equal and opposites, so their magnitudes here are equal. Okay, and that will be equal to mu times v relative. Okay, mu times v relative. Also we learned like kinetic energy in center of mass frame will be given by half mu v relative square. Okay, so this we have already learned. We will use all these relationships in order to discuss the collision in C frame. So in C frame, when we will be looking at this situation, how will it look like? So this would be, let's say, vector P1 tilde, and this would be vector P2 tilde. So they are equal and opposite. So for elastic collision, we know that kinetic energy in C frame initially, or simply let's use the dash sign over here, kinetic energy initially will be equal to k dash tilde, that we know. So you looking at this relationship, what we can say that v relative is going to constant. Okay, so before and after the collision, as long as the collision is elastic, the relative velocity of the particle, colliding particle, is not going to change. V relative, or in fact the magnitude of v relative is going to be constant. Okay, in head-on collision the direction is along this line, so v relative is going to be constant. That means the magnitude of let's say p1, looking at this relationship over here, like p1 tilde, its magnitude will be equal to p1 tilde dash, that will be equal to mu times v relative, because v relative is not changing. So the magnitude of p1 dash will be equal to magnitude of P1 in center of mass frame. So this gives us only one possibility, since during the collision the impulsive forces has acted, and it will be responsible for change in direction. So we have only one possibility. The impulsive forces is going to act along this line in case of head-on collision. So that means the condition after collision, means linear momentum after collision in center of mass frame, is only going to reverse its direction. So this vector would be p1 dash tilde, and this vector here would be p2 dash tilde. So the relationship which we are looking at is uh, p1 dash tilde is equal to minus p1 tilde. So this also gives us that v1 dash tilde is equal to minus v1. Okay, so this relationship, and similarly we can have a relationship for v2 as well. So we can say v2 dash tilde would be equal to minus v2 tilde. So now coming back to our initial objective. So our objective was to find out v1 dash and v2 dash. So let's first try to find out v1 dash over here. So v1 dash is going to be equal to, you can say that the vc, using the vector law of addition, so vc plus v1 dash tilde, that we can safely write. And according to this relationship over here, v1 tilde, so vc minus v1 tilde we can write over here, and v1 tilde we can very safely write, that would be vc, and v1 tilde would be nothing but v1 minus vc. Okay, so this gives us v1 dash will be equal to 2 times vc minus v1, and similarly v2 dash will be equal to 2 times vc minus v2. So I hope you people have understood these two relationships, and let's see in one simple example that how, looking at center of mass frame, this problem has become very easy for us. So let's take one example, very simple example. This example you can solve in center of mass in ground frame also, but see, solving it in center of mass frame, how simplified it has become. So let's take one example. So say we have two particles of mass m1. Let's say mass m1 is say 2 kg, and mass m2, let's take an example of, let's say that is 1 kg. And let's take before collision, the velocity of m1 was, let's say in rightward direction, that was equal to 3 meter per second. And for m2, let's say its velocity before collision was say 1 meter per second. So we are interested in finding out that what would be the value of v1 dash, velocity of m1 after collision, and what would be the value of v2 dash over here. So these two things we are looking for, and we already have a very simple formula over here. So that would be v1 dash is basically according to this formula over here, that is 2 times vc. Okay, so before that we should calculate vc. So vc here would be m1 v1, that is 2 into 3 plus m2 v2. So m2 is 1 kg, and v2 would be minus 1 divided by m1 plus m2, that is 2 plus 1. So this gives us 5 by 3 meter per second. So 2 times vc, we can say that would be 2 into 5 by 3 minus v1, and v1 is basically 3. So this gives us our result as 1 by 3 meter per second. Okay, and similarly v2 dash would be 2 into 5 by 3, and v2 dash is basically minus 1 over here. So this becomes 13 by 3 meter per second. Okay, so after the collision, this body will be moving in this direction with this velocity, and this body will be moving in this direction with this velocity. So look how simplified this problem has become when we have started looking at the collision in center of mass frame. So this was an example of head-on collision. I hope from the next time onwards, whenever you get such kind of case, you will be using this formula over here, these formulas. So now let's look at oblique collision. In center of mass frame, we will be looking at. Okay. So oblique collision, and we will also be taking the nature of collision to be elastic one. And here we will restrict our discussion to one specific case scenario only. Okay, and that case scenario is, let's say this is some M1 and this is some M2. So M2 is say some target which is at rest, and M1 is some bombarding particle and its velocity is v1 before the collision, and it goes strike M2 obliquely. Okay, so when it will start obliquely, hit the target obliquely, after the collision, maybe M1 will fly in this direction and M2 will fly in this direction. Okay, depending upon the impact parameter and all. So basically, after the collision, okay, let's say after the collision, let me use some other color pen over here. So after the collision, it would be moving with linear momenta. Let's say P1 dash and M2 will be moving with linear momenta P2 dash. So our problem statement is to find out P1 dash, what would be P1 dash, and what would be P2 dash. These two are vectors over here. So we will be looking for its magnitude as well as direction over here. So let's try to look this problem in center of mass frame in C frame. So in C frame, like we previously did, okay, so what we can say, so in C frame, let's say the linear momentum of M1 before the collision would be P1 tilde, and obviously the P2 tilde, that is a linear momentum of body 2 before collision, would be equal and opposite of P1. So this is the condition before collision, and the condition after collision, you can say we have already seen, like in elastic collision, there will be no loss of kinetic energy. So K tilde will be equal to K dash tilde. So that means like P1 tilde will be equal to P1 dash tilde in magnitude. Okay, so uh, so P1 tilde dash, this quantity over here, this vector over here, will only change the direction and will not change its magnitude. So let's say this is um, P1 tilde. So the condition will look something like this after collision. So let's say this is P1 tilde dash. Okay, let's say from its initial direction, it has got deviated by an angle of theta tilde. Okay, so if P1 tilde is like this, so you must realize that P1 tilde dash will be equal and opposite of P2 tilde dash. So P2 tilde dash is going to look like this. That would be P2 tilde dash. So I hope you understand this diagram very well. So now our requirement was to find out uh, P1 dash and P2 dash respectively. So let's first find out P1 dash. So P1 dash, we can write it as M1 times V1 dash. Okay, and V1 dash can simply be written as M1 times Vc plus V1 tilde dash, and that will be equal to M1 Vc plus M1 V1 dash tilde. So that would be P1 dash tilde. So that is P1 dash is equal to this quantity. P1 dash is equal to, simply we can write M1 Vc plus P1 dash tilde. So that is, say, equation number 1. And similarly, we can write P2 dash is equal to M2 times Vc plus P2 tilde dash, that would be equation number 2. So if we add both these equations, so what we will be getting is P1 dash plus P2 dash is going to be M1 plus M2 times Vc plus P1 dash tilde plus P2 dash tilde. And you must realize, since P1 dash and P2 dash are equal and opposite vector in center of mass frame, so this quantity is going to be 0. Okay, so this is going to be M1 plus M2 times Vc. And you must realize also that first of all, let's write this relationship P1 plus P2 dash, because that is going to be very, very important for us. So M1 Vc plus M2 Vc, let's say that is equation number 3. And similarly, like P1 dash plus P2 dash tilde, okay, will be M1 plus M2 times Vc. And Vc in that case, velocity of center of mass in that case, before and after collision, it is going to be same due to conservation of linear momentum. And this we can simply write as M1 V1 divided by M1 plus M2, and this term will get cancelled and we will simply be getting M1 V1, which is equal to P1. So let's say that is equation number 4. So we are going to use these equations in order to analyze the problem afterwards. So don't be confused, okay, by looking at so many equations, because the final result we would be looking at will be quite simplified. But before going into this, we need to look into the smaller details over here. So now there is something called triangle diagram. Triangle diagram of momentum. Okay. So please carefully try to learn this diagram. So how we are going to draw this diagram. So that is very, very simple. Please try to listen carefully and learn. If you listen carefully, I guarantee you will be very comfortable with this. So first what we have to do, we have to draw a vector P1. Okay, and before doing that, let's write all the relevant equation which we derived in the previous page over here, so that we can have everything in the same page. So we derived one thing is like P1 dash was equal to um, let's look at the relationships what we. So P1 dash is equal to M1 Vc plus P1 dash tilde, and P2 dash is equal to M2 Vc plus P2 dash tilde. And we also derived that P1 dash plus P2 dash is equal to P1, and we also derived like P1 dash plus, or simply let's say this quantity was nothing but M1 plus M2 times Vc. So here this vector P1 we have drawn. Okay, so let's name the endpoints, so A and B. Okay, now what we can say, let's choose one point here, some point O, which divides the line AB in ratio M1 is to M2. For example, AO by BO, we want it to be equal to M1 by M2. Okay, so in that case, this vector is going to be M1 VC and this vector is going to be m2 vc, because we see like p1 is equal to m1 vc plus m2 vc. We can very clearly say that AO vector is m1 vc and OB vector is m2 vc. So now what we have to do is taking OB as radius and O as center, we can draw a circle. Okay. So this circle here is centered at O and its radius is OB, which magnitude is equal to m2 vc. Now what we have to do here is we can take a point C anywhere on the circumference of this circle, and we can say like this vector over here would be p1 dash tilde, and equal and opposite vector over here would be p2 dash tilde over here. So now looking at this situation over here, like you can see that using triangle law of vector addition, since we can see m1 vc plus p1 dash tilde, m1 vc plus p1 dash tilde, so this vector over here is nothing but p1 dash. And also you can say like p2 dash tilde, this is p2 dash tilde over here, and this is plus m2 vc, so this vector is going to be p2 dash. Okay, so now along AB, this was the direction of initial motion. Okay, and in center of mass frame, what we can see over here, in center of mass frame, the particle 1 has got deviated by, let's say, some angle theta tilde. Okay, and like p1 dash vector and p2 dash vector are in ground frame of reference. So in ground frame of reference, the deviation of particle 1 would be, let's say, something called theta 1. Okay, and there is one another important thing which we are interested in, that what would be the scattering angle of the of between p1 dash and p2 dash after the collision. So this angle phi we are looking for. So these things are matter of interest for us. And now one thing you have to notice in this diagram, okay, is uh, what I have already assumed, that OC is equal to OB. So can we justify this as well? For example, OC is equal to OB, whether it is true or not. Like for example, OB here you can see is nothing but M2 VC, and VC is nothing but M1 V1 divided by M1 plus M2. Okay, and m1 m2 divided by m1 plus m2 is nothing but mu, and v1 here is nothing but v relative over here. So that is definitely the magnitude of p1 dash tilde is equal to p2 dash tilde, which is the vector OC over here. So definitely OC is equal to OB over here. Again, I am going to repeat this thing, what were the procedure of drawing this triangle. First, we draw vector P1, and AB line we divided into ratio M1 and M2, and here is point O, and we draw a circle, okay, having radius OB and center O, and point C is going to lie anywhere. It can lie anywhere depending upon the situation. Okay, so theta dash, theta tilde can be anywhere. Okay, so I hope this diagram is clear. So now we will be looking at some special cases, okay, presented by this triangle diagram of momentum. Okay, so let's look at those situations one by one. So first of all, let's talk about case 1. In case 1, let's say M1 is less than M2. Okay, so again I'm repeating the procedure. So let's say this is you can say the vector P1, that is A and B, and since M1 is less than M2, point O is going to lie somewhere over here, so that the AO distance is smaller than OB distance. Okay, so now our circle will look something like this, which would be centered at O. Okay, and point C would be lying anywhere here. So this, you can say, is P1 dash tilde, and this vector over here would be P1 dash, and this vector over here would be P2 dash, and this angle over here is theta tilde, and this angle over here is theta 1. Okay, and say this angle here is phi. Okay, so looking at this situation, theta tilde can attain any value between 0 to pi. Okay, like, because point C can lie anywhere on the circumference of this circle. So depending upon this, what would be the range of values of theta 1 that can attain? Okay, so theta 1 would be minimum when point C coincides with point B. In that case, theta 1 will be equal to 0, and the value of theta 1 would be maximum when point C lies diametrically opposite of point B. Like, for example, over here. So in that case, we can say that theta 1 can be anywhere between 0 to pi over here. And just by looking at the diagram, you can see that phi 1 would be nothing but, phi 1 would be nothing but, that would be always greater than pi by 2 over here. One more thing here I want to relate, like, for example, the relationship between say theta tilde and theta 1, etc. This relationship I want to establish. So that relationship can be established using simply triangle law of vector addition. So tan theta 1, we can simply say that would be the magnitude of this line. This line is basically same as this. So this is basically M2 VC, and this here is M1 VC. So tan theta 1, we can write it as simply M2 sine theta tilde divided by M2 cos theta tilde plus M1. Okay, so this is the relationship between theta 1 and theta tilde, which are respectively the angle of deviation of the bombarding particle in center of mass frame and in ground frame. Okay, so here in case 1, we can see that the theta tilde, okay, since it can have any value between 0 to pi, theta 1 would be lying between 0 to pi in this specific case scenario of m1 less than m2, and phi 1 would be greater than pi by 2. Okay, you can use the above relationship which we have written in order to get the value of phi 1 also. So now let's say the case 2, let's discuss case 2. And this case 2, say m1 is equal to m2. M1 is equal to M2, and that is quite interesting case scenario. So first we will be drawing the vector P1, okay, which would be AB. And since M1 and M2 are equal, the point O would be the midpoint of AB, okay, and we can draw the circle. So AB here would be nothing but the diameter over here, okay, and point C could lie anywhere on the circumference. So this is P1 dash tilde, and that is simply P1 dash, and this is P2 dash, and this angle is theta tilde, this angle is theta 1, and this angle is phi. So you can see very well, looking at the geometry, that this angle ABC is a right angle triangle having this angle as 90 degree. So it is very clear for us, like theta 1 is going to lie between 0 to pi by 2, and the value of phi would be nothing but exactly be equal to pi by 2. That is quite very interesting case. So if mass of the colliding particle is equal to mass of the bombarding particle, we can definitely say for sure that m1 and m2 will be flying in mutually perpendicular direction after the collision. So that is very very interesting case. So now let's look at another interesting case, that would be case 3. And in case 3, m1 this time would be greater than m2. So how will the triangle diagram will look like in this case? So let's say this is vector p1 over here, and since let's draw a little longer one, and so this is A and B. So since m1 is greater than m2, point O will lie somewhere over here, and this is how the triangle, the circle here will look like. So now point C could be anywhere. Let's say a point C is here. So in that case, this one would be P1 dash and this would be P2 dash vector. So like we are interested in the range of theta 1. So like uh, where should this point C lies such that this angle over here is maximum? So obviously we can draw a tangent over here. So if point C lies somewhere over here, so in that case, this would be P1 dash and this would be P2 dash and this would be P1 dash tilde. Okay, so in that case, this angle would be maximum possible value of theta 1. Okay, so looking at the geometry over here, looking at the geometry of this case scenario, let's look in this triangle. So this is definitely, this is a tangent, so this would be a right angle triangle. Okay, and the magnitude of AO side is definitely m1 VC, and the magnitude of OC side would be same as magnitude of OB side, which is simply equal to m2 VC. So sine theta m, we can definitely write for sure that would be m2 by m1. So we can say theta m is nothing but sine inverse m2 by m1 over here. So that is the maximum deviation, okay, the bombarding particle can suffer uh, in this case scenario when m1 is greater than m2 over here. So theta is going to lie anywhere between 0 to theta m, and in this case scenario, this angle phi, you can definitely see that phi is less than pi by 2. So these were three interesting cases, and mainly if in exam you are asked question on this, your question will be from either of these three cases. Okay, so let's try one simple question over here. So let me open one question for you. Uh, okay, this. So here we are having a question. It says a sphere of mass m, a sphere of, say, mass m collides with another stationary particle of mass m by 2. So you can say that m1 is equal to m and m2 is equal to m by 2, and the collision is oblique. Both the spheres are smooth and there are no external force acting on them. Maximum angle, we are required to find out the maximum angle through which sphere of mass m can be deflected with respect to initial direction of motion. So this is the initial direction of motion. So just by reading at the questions, since we have discussed this just now, so you must understand. So basically they are we are looking at this specific case when m1 was greater than m2, and here they are asking you basically theta 1 maximum, and theta 1 maximum, we just have derived that this is equal to sine inverse m2 by m1. So m2 by m1 in this case you can clearly see that is equal to 1 by 2. So this is going to be equal to pi by 6, and this pi by 6 would be our answer over here. So look how simply we are able to solve this problem in center of mass frame. And in ground frame, this problem would have been really difficult. Looking in ground frame of reference, that problem would have been really difficult. You can try it by yourself, but in center of mass frame, see how simple it looks like. So that is the advantage of center of mass frame in some cases over ground frame. Okay, so here we discussed about center of mass frame, and so most of the important aspects of collision we have already discussed. Okay, so before we end this session, it would be very beneficial for us to look into some specific models of problem which comes in our exam IIT JEE quite frequently. So let's look into some models of problem, and those models will be basically based on principle of conservation of linear momentum. Okay, so let me open some question for you. Okay, so this is the problem. So what we are having here is uh, a nucleus at rest disintegrates into two daughter nuclei with no other particle emitted in the decay. So there is some, say, parent nucleus, okay, which disintegrates into two daughter nucleus. Okay, and their masses are also given. Their masses are m1 and m2. Parent nucleus was initially at rest, and these two here, you can say, are daughter nuclei. Okay, and they have given the mass of nucleus formed are m1 and m2, and energy released is q. So in this process, the energy that has been released in q, and now they are asking what is the magnitude of momentum and kinetic energy of the two products. Okay, uh, and we have to assume in this discussion that the energy released is converted into the kinetic energy. So whatever this energy q that has been released over here, that will be shared by the daughter nuclei of masses m1 and m2 in form of their kinetic energy. So after the collision, since initial linear momentum is equal to 0, they will be basically flying in opposite directions such that their linear momenta are equal and opposite, because initial linear momentum were equal. Okay, so what we can say, that after decay, the first thing we can say, that the linear momentum of the particle 1 would be opposite of linear momentum of the particle 2. That is from the conservation of linear momentum we can say, and we can definitely say for sure that their magnitude will be equal. Okay, And looking at that, let's say M1 has kinetic energy K1 and M2 has kinetic energy K2. So the magnitude of P1, you can always write it as 2 root under 2 M1 K1, and magnitude of P2 can write it as root under 2 M2 K2. So this gives us K1 by K2 will be equal to M2 by M1. Now, let's say this is our first equation. And the energy balance equation which we will be looking at is, see, since kinetic energy of K1 and kinetic energy of K2 will sum up to the energy that has been released in this process, because this energy released will be divided by M1 and M2 in form of their kinetic energy. So this is our equation number 2. So now looking at that, equation number 1 and equation number 2, we can very easily say that K1 would be nothing but M2 divided by M1 plus M2 times Q, and similarly K2 will be equal to M1 divided by M1 plus M2 into Q. And looking at this relationship, in fact, this relationship over here, you can clearly see that the greater fraction of energy will be acquired by the particle having the lower mass. Okay, a heavier mass will be having less kinetic energy. So this is the problem. And this model of the problem, okay, can be used, okay, to solve this result, these results. Acha, one more thing we were required to find out was the magnitude of linear momenta. Like for example, if we want to find out P1, P1 mod, magnitude of linear momenta. So since we have already found out K1, we can use this relationship root under 2 M1 K1, and the value of K1 we have already derived. So that would be M2 divided by M1 plus M2 into Q. And you remember that M1 M2 divided by M1 plus M2, we term it as reduced mass, and that will be simply 2 mu K, root under 2 mu K. So these three relationship, I must say, these three relationships which we have derived, the situation we looked at is basically there was a two particle system or two body system, we must say, sorry, two body two body system uh, having masses which was initially at rest, we can say initially at rest. That means their linear momenta initially was equal to 0, and kinetic energy of the system was also equal to 0, and due to some internal mechanism, okay, some energy was released, some energy Q was released. Okay, so now what we can say, in this case scenario, we just solved for it, and we saw that the final linear momentum, like P1, will be equal to P2, and that was equal to root under 2 mu Q, and also uh, K1 was equal to M2 divided by M1 plus M2 into Q, and K2 was equal to M1 divided by M1 plus M2 into Q. So these results, okay, can be used, directly used into a broader category of problems involving these case scenario. Two body system, and initially it would be at rest, such that the initial linear momenta of the system is equal to 0, kinetic energy is 0 as well, and somehow due to some internal mechanism, some Q energy is released. Okay, so we can use these relationships, like for example, uh, before looking into the real problems, some model of problems we can solve using this is, for example, quite frequently seen models. Let's say there is some spring, let us say, and two bodies of mass m1 and m2 is connected, and spring is initially compressed, let's say, and the whole system is initially at rest. When the system is released, okay, and when the spring is at its natural length, in that case what would be the linear momenta of body 1 and body 2? Okay, so in this situation you just have to observe that the value of q here would be equal to the energy released would be the spring potential energy, so that would be half kx square. Okay, and this relationship you can use, and mu, the value of mu will be equal to m1 m2 divided by m1 plus m2, and q simply you can use as half kx square. And also at this instant you can find out the value of k1 and k2. Another example, another simple example, for example, this kind of case we often look at. Okay, so this is body of some mass m1 and some another body is released at m2. So let's look at this problem more properly, since we have some time left. So it would be better for us to look at the exact problem which appeared in JE 2017. JE Advanced 2017. Let's look at this problem. So here comes the problem. So what we are having, looking at the diagram, you can see, looking at the diagram, so we are having a block of mass capital M which has a circular cut with a frictionless surface as shown. The block rests on a frictionless horizontal surface of a fixed table. So this is a frictionless horizontal table, and this is fixed. Initially the right edge of the block is at x is equal to 0. This is the right edge, and this is at x is equal to 0 in a coordinate system fixed to the table A. Point mass m is released from rest. So some point mass is released from rest over here at the topmost point of the path as shown, and it slides down. And when the mass loses contact with the ground, when this body comes here, okay, when it loses contact here, when the mass loses contact with the block, its position is x and uh, its velocity is v, and at that instant which of the following options are correct, that we have to find out. Okay, so let's try to look at each and every option one by one. So basically in these options we can see the velocity of point mass or velocity of the block. So they are interested in finding out the final velocity of each element of this system, and they in option B and C you can say they are asking the x component of displacement and position, etc. So they are interested in position or displacement you can say, and their velocities finally. So we have already discussed the results in these case scenario, and we will be using these results in this. So first of all, let's try to find out the position. So looking at this system you can see that the net external force in horizontal direction, since this the surface is frictionless, net external force in horizontal direction is going to be 0. So acceleration of center of mass along x axis is going to be equal to 0. So velocity of center of mass is not going to change, and it is going to remain 0 as well throughout the motion along x-axis. Okay, so the displacement of center of mass will also be equal to 0. So let's say this is body 1 and this is body 2. So what we can say over here is m1 delta x1 plus m2 delta x2 is equal to 0. And delta x1 delta x1, let's say when this body will be moving rightward, this particle is moving rightward, so this block will be moving leftward, let's say by some value. say delta x1 would be um, say let's say x1 over here, and we can clearly see that delta x2 with respect to 1, clearly like the initial position is this and the final position is this, so this would be the displacement of this particle with respect to this block uh, in along the horizontal direction. So this is going to be r over here. So delta x1 here, let's take care of the direction also, that is going to be minus x1. So delta x2 in ground frame of reference would be the vector sum of these two quantities. So that would be r minus x1. We have already solved a problem of this nature, and substituting this value, we can say that x1 here will turn out to be equal to m divided by capital M plus m into r over here. So this would be the displacement. In fact, minus x1 is the displacement. So the x component of displacement of center of mass of block is going to be minus mr divided by m plus m. That option is definitely correct. And looking at the position of point mass is x is equal to minus root 2 mr m plus, let's explore this option number c. So the position, the final position of block m2 we are looking at, so x2 would be, x2 final would be nothing but x1 final plus let's say delta x1 we can say. So x1 final is going to be, x1 final is going to be that is x1 initial. So x1 initial is basically minus r over here, and delta x1 we have just found out it to be equal to m r divided by m plus m. And that you can see that option c is not correct. And looking at the option A and B, the velocity of point mass is v1. So the linear momenta, we can say, let me use some other color pen. So linear momenta of this particle here, uh, finally we will be using that formula, P is equal to root under 2 mu q, and q here will be equal to the energy released here would be simply equal to mgr. So this is the linear momenta along the horizontal direction of body 1 and body 2 as well. That is mgr, I must say. So that will be equal to the velocity we can find out. So v1 would be p divided by m1, and p here is uh, 2, and mu is basically small m capital M divided by capital M plus small m, uh, into q is basically mgr. Okay, and that divided by m1, which is basically um, capital M over here. So um, velocity of the point mass they are asking. So this is m2, so this is going to be m. So solving this thing will get cancelled, and we will be uh, definitely getting this result A. Okay, and the velocity of block capital M, this option definitely does not seem to be correct. Let's explore let's look at it quantitatively also. So v2 so that is v2 we have found out, and v1 would be p divided by m1, and p divided by m1, p is nothing but 2 m square capital M to gr divided by capital M plus small m, divided by, here it would become capital M. So this is definitely not that result. So this option D is incorrect. So here we have discussed about um, some this specific model. Okay, and these results could be easily used to derive the result quickly. Okay, so let me stop sharing my screen with you people. Stop sharing so we can get face to face. Okay, so now see, in these three lectures we have discussed the concept of center of mass and collision and conservation of linear momentum. And in the coming sessions we will be discussing about rotational properties of rigid bodies. Okay, so I bid goodbye over here. Have a good day. Thank you.